Three areas of good house design are closely tied together: letting the sun warm the house in the cooler months, avoiding summer overheating, and getting the thermal envelope right to maintain the ideal temperatures inside. For many parts of New Zealand, getting this right can result in comfortable, year-round internal temperatures of around 18 to 25 degrees. There's a growing number of homes in both the North and South Islands that are so well designed for the sun and have such high levels of insulation they rarely need to use any heating at all. They might use a heat pump no more than half a dozen times over the whole of winter. That means they have a smaller carbon footprint, and the occupants save a lot of money over the years from lower energy bills. For maximum solar gain, the glazing of the living areas should face within 20 degrees of true north, with a shallow east-west floor plan. Getting a sun path diagram, for example from NIWA's Solarview tool, will help a lot. It shows the position of the sun on the site at different times of the day and year. BRANZ modelled indoor temperatures of more than 200 recently built houses and found those that didn't take advantage of solar design needed up to 3 times more purchased energy to keep temperatures at a comfortable level than those who did. That's a very expensive wasted opportunity. Of course, you also need to make sure the house doesn't overheat in summer. Eaves or other external shade devices are important on the northern side of the house, with vertical shades on the east and west faces. Ideally, these shading devices should be movable within the seasons. The next step is to use wall, roof and floor details that keep the building warm in winter and cool in summer. Using high-performance construction details is an excellent investment in a more comfortable home. The upfront costs might be higher, but over the lifetime of the house, running costs and carbon footprint will be considerably lower. Using thermal mass to keep a house warm works by allowing sunlight to fall on exposed, high-density materials, such as a polished concrete floor slab. The heat absorbed during the day is then released as the temperature cools at night. To be most effective, it needs careful design using a thermal simulation software tool. The most critical part of good thermal performance comes from windows and glazing. In an average insulated New Zealand house, more heat is lost through the windows than through either the roof or the walls or the floor. There are 3 important considerations for windows and glazing: location and size of windows, external shading provided, and thermal characteristics of frame and glazing. In general terms, windows should be larger on the north side, ideally where living spaces are, with external shading devices such as eaves to reduce midsummer overheating. Tightly controlled or with movable shading devices on the east and west sides to reduce summer overheating, and as minimal as possible on the south side to avoid winter heat loss. Building code minimum requirements for windows are being beefed up. The basic aluminium-framed double glazing with no special features won't comply with the new schedule method minimum construction values, even for the warmest climates. Designers have a handy tool here, the Window Energy Efficiency Rating System, which compares the thermal performance of windows, considering frame, glazing, and size. Part of good design of the thermal envelope is creating a reasonably airtight envelope that allows good control over ventilation. In simple terms, build tight and ventilate right. Of course, every house should have mechanical extract ventilation to remove moist air from kitchens and bathrooms, but many houses will also benefit from an energy-efficient mechanical ventilation system, such as a heat recovery ventilation system. Passive ventilation is an option, but needs to be very carefully designed and is harder to control. How do you know you've found the optimal design of the thermal envelope? The only way of achieving this with certainty is with thermal simulation. This is modelling the thermal performance of the building as a whole, taking into account energy flows through all the building elements and between the internal zones. A whole host of different influences on performances can be tested: solar orientation, shading, construction R values, and so on. Different options can be tested and changed until the best results are achieved.